Lawrence a year before I did, actually, from, God, I can't even remember, Keegan?
Yeah.
Sure, Illinois. Anyway, and so he's quickly decided that, you know what, as soon as I got here, he was like, whoa, PChem. Spread the word, it's really fun. Anyway, so he's like, I want to be your guys' check. I want to be a research student, I don't know. He likes Rush, and I'm a Tom Petty fan, but I can do it. But then he was so dedicated to the track team, actually, and he actually was part of a group that worked with getting athletes to go to the conservatory performances and con students to go to athletic performances, well, athletic things. And so while he was doing all of that, he comes to me and he goes, hey, I got an idea, astrochemistry. I'm like, oh gosh, how the hell are we going to get astrochemistry to the liberal arts? And here we are today. And so this is what Tyler's going to tell you about, bringing astrochemistry to the liberal arts via quantum calculations.
Thank you. So yes, I am Tyler. Thank you all for coming. As Allison said, I will be bringing astrochemistry to the liberal arts using open source quantum calculations. So sitting in the audience, you might be wondering, what is astrochemistry? Put simply, it's the chemistry of things in space. Astrochemists seek to explain the chemistry of astronomical observations. It's an interesting discipline of chemistry because it involves a lot of interdisciplinary involvement. So it involves chemistry, astronomy, physics, and biology. It's interesting to me because I am quite a fan of interdisciplinary fields. Anyway, so astrochemists use observational data from telescopes, they use laboratory recreations of systems in space, and they use computer modeling to do astrochemistry. So, with an interest in astrochemistry at a small school like Lawrence, where we don't really have any access to astrochemistry courses or anything like that, I decided, how am I going to study this? And so we don't have telescopes, so we can't look at observations. We can't exactly recreate a very low temperature, low pressure system, and so we turned to computer modeling to try to get astrochemistry here. So, last summer I presented at the 250th American Chemical Society National Meeting in Boston. And while I was there, I was seeking out astrochemists. And one of the people that I met there was Ryan Fortenberry. He's a professor at Georgia Southern University. Professor Fortenberry is part of a collaboration with other scientists on a quantum calculations software that is open source and web-based called Psi4. So being open source means that it's free, and being web-based means that we can access it from anywhere. We can do computations from pretty much anywhere. As I met Ryan, I was introduced to this. It was like, hey, this is a relatively easy to use, easily accessed calculation software. So I said, we don't have a lot of computational chemistry exposure here at Lawrence either. So I said, let's see if we can try to bring this to Lawrence. So, what are quantum calculations? The quantum calculations yield what we call atomic orbitals. So here we have a nucleus of an atom, and we have surrounded by the nucleus is our protons and electrons. If we're looking at a hydrogen atom, we have a proton and an electron. And so the orbital essentially models what we call the probability of density. So there's an electron surrounding the nucleus, and there is a probability of finding the electron somewhere within the area around the nucleus. And it's represented by the spherical shape that we call an orbital. So orbitals answer two questions for us. Where is this electron? Or what is the probability of finding an electron at some point within the orbital? And they also answer, what is the electron's energy? Because electrons have energies. So we have our atomic orbitals. We can combine atomic orbitals to form molecular orbitals. So we're talking about single atom, we're talking about multiple atoms for a molecule. So we take these two electron clouds with the electron, or the probability distribution of those electrons. We take these two clouds and we combine them together, and so as the nuclei approach each other, the two orbitals that demonstrate the area we can find the electron, they overlap. And so we're left with a new electron density, which we see in the molecular orbital. So molecular orbitals are more complex than atomic orbitals. However, we rarely work with a single atom system, so we need molecular orbitals to describe most systems that we're interested in. So, why do we need quantum calculations for this? So from the previous slide, we have those two atomic orbitals combining to form a molecular orbital. And we see that they're represented here by this red sphere. So remember, from orbitals, we have that electron cloud. We find the electron within the area there. And they yield their energies. And so when I say energies, we can quantize those energies. So here we have different energy states that increase as we go down. So all of these shapes, these red and blue shapes, you may be familiar with if you took isochemistry or chemistry here. These are all atomic orbitals. So these are similar to this orbital. So much like we can combine a 1s orbital, a spherical orbital, with another one to form a molecular orbital that we see up in the corner, we can also combine this type of an orbital with another orbital to form much more complex molecular orbitals. We can also combine more than two. We have multiple atoms in a molecule. And so you can imagine that as we combine more orbitals together, our overall molecular orbital can become very complicated. So to pull any information out of that, we're doing some kind of a calculation, it becomes very difficult to do by hand, and so we need a computer to do it. So, what are these shapes? We've seen them before. We say they're orbitals. Where do they come from? It turns out they're solutions to Schrodinger's equation. So Schrodinger's equation has to do with what we call the wave function. Wave functions contain information about the electrons, and they describe the orbitals. So, wave function contains information. We access the information that the wave function yields to us through using what we call an operator. So here we have the Hamiltonian operator specifically, which is a total energy operator. And so you apply the operator to this wave function, and it yields an energy. Or it yields an observable, which in the case of the Hamiltonian is energy. So if we think of psi, which is our wave function, sorry, I should mention that psi, wave function is represented by the Greek letter psi. If we look at our wave function as, say, an oracle, then we ask the oracle a question, and it yields an answer. So the wave function is an oracle, the operator is the question we ask it. Well, it turns out that there are, when we're looking at wave functions, we can't always know for certain what wave function describes a system. So we have several wave functions that may describe it, and we have to sort of, we have to make approximations about those wave functions in order to get energy values. So the question is, which wave functions are we going to use in our calculations? Or which oracle are we going to ask the questions to? And which operators are we going to apply to pull out whatever observables we want? So, how do we do that? So, we have a flow chart starting with, we need to build a molecule. So we're doing some kind of a quantum calculation. We start with a molecule that we're interested in. And then we have to determine what approximations we're going to make about the orbitals, about the wave functions involved. So this is essentially, we're picking which wave functions we're going to, which wave functions are going to affect the orbitals more. And so we approximate a wave function, and then we use that approximation to solve that Schrodinger's equation. So we have a sort of a guess wave function, we apply that operator, we get an energy. This is just a simulation. In order to actually know what energy a system is producing, we have to use experimental data. So we should have, for any kind of reaction that we're looking at, we have a resultant energy value that comes from experiments. So we make an approximation, we solve the equation, and then we compare it to the experimental data. And we say, were our approximations valid? Is our energy value close enough to an experimental value? And if not, which is usually the case originally, we have to change the approximations that we make. So we have to change what, which wave function we're going to be looking at. So it's sort of like if we go back to that oracle example, it's sort of as if because we have the experimental value for energy, it's sort of like we know the answer to the question that we're asking, and we're we're basically looking around at different oracles and asking them all the question, and whichever oracle gives us the answer closest to the answer that we know is the answer, is the oracle that we work with. So in other words, we're basically changing our approximations a bunch of times until we get a satisfying energy value. So we change our approximation, we run it through Schrodinger's equation, get a new energy. We do this several times until we get a satisfactory result. This becomes expensive in several ways. It can be difficult for a computer to process this kind of a computation, especially as we talk about more complex molecular orbitals, that it takes a lot of computer processing power to run a calculation. And so if you're taking, say, running through Schrodinger's equation, the computer takes, let's say, 2 hours to do that, and you run through it 20 times, you're losing up to days of time and spending a lot of resources and computations doing that. But eventually, we do get some satisfactory energy value. And from there, we can pull out other properties of the chemical system. That's what chemists care about. So, the title of the talk is bringing astrochemistry to liberal arts. So how are we actually doing that? How am I actually doing that? So we talked about this quantum calculation software that we found through Ryan Fortenberry. And so I want to bring this to Lawrence. I'm also interested in astrochemistry. So I need to find some way to take some sort of astrochemistry reaction or system or something like that and perform some kind of calculations on it using this open source software. So that's basically what my project is. Well, it turns out that the Sci4 developers have produced labs for students to do at universities that allow the students to gain experience with computational chemistry and also allow the programmers to sort of advertise their code and software, and it also provides them with feedback because the students will do a lab and they will determine how, what sort of change they want to make to their code as a result. So we thought, let's contribute a lab to Sci4. And so in most of the previous labs that already exist on their website, they do simple quantum calculations. So they say, take some molecule, find its energy, and then you're done. So we said, let's try to take that a step further. So we said, let's find an energy, and let's relate it to some other chemical property. So what kind of a good chemical property can we look at? Well, there's a lot of reactions happening in space. And so we decided, let's look at reaction kinetics. So we brought that idea to Ryan, and he said, go for it. So we set out to develop a lab involving some sort of astrochemistry thing, and then using our quantum calculation software to answer a question about kinetics. So we need some kind of a molecule to study. We need to look at, or question what kind of properties we're interested in. So we're talking about kinetics, but what part of kinetics are we going to look at? And we also need some kind of a reaction which demonstrates these properties of the molecule. So we decided to look at hydrogen cyanide, shown in the corner there. Hydrogen cyanide is found in space on Titan and in comets, so it's an astrochemical. And it contributes to forming amino acids, which are essential to life. So we see by this chart here, we have hydrogen cyanide, and we have glycine forming here. They're thought to contribute to amino acid formation. And additionally, it is only 3 atoms in size, so it is relatively simple, which means that the calculations that we conduct on it will take less time, and it'll have a simpler orbital model, essentially. So, hydrogen cyanide should be good for a lab. Well, then we have to ask, what are we going to ask of the molecule? I said we're looking at kinetics. So let's review chemical kinetics. So here is a plot of a reaction occurring from left to right, so we go from products to reactants, and we have our energy plotted along the way. So we have an initial energy here, and in order to get the reaction to a completion, we have to overcome this hill, in a sense, until the reaction will proceed spontaneously. So we have to put in some sort of activation energy in order to get the reaction to get this far along, and then we can get it to proceed spontaneously. So we label the activation energy as the change in what we call the Gibbs free energy. And so this is the Gibbs, essentially, the Gibbs activation energy is what we will call this. And so at the peak energy in this reaction, we have what is called the transition state. So the transition state is the point in the reaction essentially where the reaction will proceed spontaneously. So Gibbs energy is related to spontaneity. And so from this, we can pull out a rate constant, which will tell us about the speed of the reaction. So here we have a rate constant, k, and it is involved in a rate law such as this, where we can relate the rate constant to the rate of the reaction. So, for the purpose of our experiment, our rate constant is given through this equation where we have Boltzmann's constant, Planck's constant, a gas constant, and then temperature and this Gibbs energy, which is the same as the energy here. So this is activation energy. So luckily these 3 are constants, and we hold the temperature constant as well. Actually, we don't get to choose the temperature. The limitations of Sci4, the software that we use, are such that it doesn't allow you to change the temperature. What that means is that for this equation, there's really only one thing changing, which is the Gibbs energy. So we can relate the Gibbs directly to the rate constant through that equation. And then we can learn about the rate of the reaction from that. So, a good reaction to model, because hydrogen cyanide takes part in a lot of reactions. A simple reaction is what we call an isomerization. So an isomerization reaction, you basically take the hydrogen cyanide molecule, and for simplicity's sake, I'll say you just take the hydrogen atom and you start moving over the top of the molecule until it reaches the other side. So here it's bonded to the carbon, over here it's bonded to the nitrogen. And so in between, so as we change this bond angle, we can record the energy so if we change the bond angle in increments, so we say we start at 180 and we start changing the bond angle in increments, we can measure the energy at each of those angles. And then we can plot those energies. And at some point we will observe some kind of peak energy where the molecule is least stable. And that is what we call the transition state. So we can then relate that to the rate law, which is specific to this reaction, which is where we have that rate constant mentioned previously times the concentration of this atom, which is this molecule. This is a first order reaction because it is basically the molecule just rearranging itself. So the goal of the lab, we're trying to use the psi4, these quantum calculations, to compute energies at each point of this rearrangement. So as we change this bond angle here, we're going to look at the energies using psi4. And then we want to determine the transition state or based upon that. So that's where we're going to have our peak energy. And then we want to take that, that information and relate it to kinetics through that equation. So again, rate constant gives free energy, energy of activation. So here's a plot of basically modeling the energy as we change the arrangement of the atoms. And so we have these sort of key points here, these inflection points, which correspond to a certain arrangement or configuration of the molecule. So I can plot these on here. So we have the nitrogen-based or nitrogen-centered arrangement, which is somewhat stable. We have our unstable transition state, and we have our very stable carbon-based arrangement. And so if I add a couple things to this plot, it starts to look a lot like that kinetics plot I showed you guys earlier. So here we have a molecule at say, the beginning of a reaction. We overcome some activation energy, and it goes to a stable conformation naturally. So we have the difference in these two energies is our Gibbs energy of activation, and the difference in these energies is the Gibbs energy of the reaction. So again, just to emphasize this, we have this equation that we're trying to get the rate constant out of. And we have this value which corresponds to this variable. So how do we actually do that? So I've talked pretty much all through at this point. At some point we're actually doing some kind of work. What are we actually doing when we're conducting this research? So we follow our flowchart from before. We have to actually build a molecule. So how do we do that? Well, it turns out that psi4 comes packaged with a 3D molecular modeling program called qWvzowllE, which basically allows you to produce a molecule in a 3D environment and then view it. So you can place a nitrogen atom, a carbon atom, and a hydrogen atom down and vary your bond angle and your bond lengths. So you can basically produce some conformation of a molecule. So that's how we build our molecule. But then we have to look at making our approximations. So as I said before, this is like deciding which oracle we're going to ask questions of. So which wave functions we're going to look at to contribute to building those oracles. And so to do that, psi4 has basically a drop-down menu where you can change the parameters. So this is basically changing the approximations we're making about the wave functions involved. So we make our approximations, and then we run a calculation using Schrodinger's equation, or rather the computer does the calculation. And then it spits out a data sheet. And so the data contained in these calculations can be used. So we have the vibrational frequencies you see up here. We have other energies displayed here. These have been used by the psi4 lab developers for other labs. But we were talking about looking at chemical kinetics. We're looking at thermodynamics, not just quantum chemistry. So we're interested in that Gibbs free energy. So we pull out that value, and we're going to relate it to the kinetics through that rate law, or excuse me, through that rate constant. So the Gibbs involved in this reaction, you notice that delta G with a double dagger and a little naught symbol. So the delta G denotes that it's a change in Gibbs energy. So as I said before, we change our conformation and we take an energy at a point. So we have an energy that's associated with this conformation, an energy that's associated with this conformation, and energy associated with the conformations in between. So the change in the Gibbs is basically taking the energy of this conformation and the energy of this conformation and find the difference between them. That's how we get delta Gibbs. And then again, we take that value, plug it in here, get a rate constant, and we can use the rate constant to build a rate law for the molecule. So, so here we have our calculation software, psi4, open source program, and we have Gaussian, which is another computations software, which is not open source. And the values that we use for comparison here are from Arthur Halpern and his group at Indiana State University. They basically conducted the same reaction, and so we use their values for comparison with ours. So we were looking to determine that transition state. So we're looking at the point at which the energy for the conformation of the molecule is at its highest. And so we basically varied this bond angle until we found that peak energy. in terms of the peak energy occurs at 60 degrees. So this angle here is 60 degrees for us. Well, they calculated it to be 72. Anyway, so we also were calculating our Gibbs energy. So we have our Gibbs energy of activation, which is the difference between these two energies, and our Gibbs energy of reaction, which is the difference between these two energies, which are displayed up in the corner here, where you see that we're at a similar order of magnitude, but there's still a bit of a difference there. However, we can take these values and our transition state angle and put them all together in a nice results table, where I can remind you that the goal of the lab was to determine the transition state. So we've done that. Determine the peak energy occurs at 60 degrees. We've used Psi4 to calculate the energy of the reaction along the way as the isomerization occurs, and then I demonstrate the difference between basically the products and the reactants and the transition state here. And then we wanted to relate those energies to kinetics. So we use this equation and we pull out rate constants, which are split up in the corner there. As a bonus, because the talk is about bringing astrochemistry to liberal arts, we've looked at a molecule that occurs in outer space. But the question is, can we relate this to astronomical observations? So we have this rate law, which is dependent on our rate constant. And we know that based on the energy diagram, we know the stability of HCN relative to HNC. So HCN is more stable than HNC, which means that when there is a formation of either HCN or HNC in, say, outer space, the molecule will prefer to arrange itself in its lower energy states. So we should see more HCN than HNC. So if we look at a ratio of HCN and HNC, we should expect this to be greater than 1. So the question is it? So luckily, there's observational data from Lucy Series, who is an astrochemist at the University of Arizona, that she conducted in 1999, where they looked at the ratios of HCN and HNC, and they found out that it is, in fact, the ratio does in fact favor HCN. So we do in fact see more of the stable molecule than the unstable molecule. So we related that to actual astronomical observations. So, was it successful? So the title of the talk is Bringing Astrochemistry to Liberal Arts Using Quantum Calculations. So have I done that? Well, now, at the end of the project, we have access to this Psi4, this open source quantum calculation software at Lawrence. So other students can gain access to basically free computations. We have conducted computations on a molecule found in space and compared to astronomical data. And we developed a lab for use in Professor Fleshman's physical chemistry courses in the future. So I would say yes, we did indeed bring astrochemistry to liberal arts. So what's next? I won't be here next year. I will be pursuing a PhD at the University of Arizona in chemistry, hopefully under the guidance of Lucy Series. So Allison will have to work on implementing the lab on her own. I'd like to acknowledge our chemistry department here. I'd like to acknowledge Professor Fleshman for her guidance over the past 2 years, Dr. Dave, who's not here anymore, and the rest of the Chem 680 folks for guidance on presenting and suggestions in the presentation. I want to thank Ryan Fortenberry and Professor Arthur Halpern, and the WebMO collaborators and Psi4 developers. And I'd like to thank Eddie Elizondo as well, because he helped me set up Psi4 on a school computer, and I want to thank the tech department for providing that computer. References? Thank you.
I think you mentioned that Psi4 is only set up for one temperature. Why would that be, and how would that affect astronomical calculations?
So part of the reason that we're looking at Psi4, that we're using Psi4, is that we can help develop it. And so other computations software, so I don't know if Gaussian can do temperature dependence, but it's currently, as far as they develop Psi4, it is only able to use one temperature, which is 298 Kelvin. So it's just limited in that it's still in development, basically. And in terms of affecting astronomical data, so the values that I calculated, we used 298 Kelvin as a temperature, but in outer space, the temperature is much, much lower. And so the values that we see are going to differ from what, or they'll differ slightly from what we would actually see in astronomical observations. Does that make sense?
And don't try to think about what temperature means for one molecule.
Right. Yes?
So you said that the calculations for the two different programs, the Psi4 and the Gaussian, were different. I guess maybe temperature, because Gaussian uses a different temperature, but what other factors could cause that change?
Yeah, so when I talk about the approximations that I make about wave functions contribute, so Psi4 may have different, or may treat the wave function in a different manner. And as we combine them in different ways, so basically we are trying to say, model this orbital in this way, based on the approximations that we're making. And so they may have different fundamental approximations built in. So that'll give us a different value, which is why we see the different bond angle, which results in a different energy. Yes?
So you compared two modelings, so two different orbitals, right?
Yes.
And so I was just curious if there's experimental values for the Gibbs free energy or the rate coefficient, because that could maybe confirm if maybe you sit right in the real numbers right in the middle.
Right. Yeah, I believe there are. We haven't actually looked at that. We were basically trying to see if we could take the experiment they did at a large university using Gaussian and do the same experiment and reproduce the results more or less using our open source program. So I'm sure there is, and that was something to look into in the future.
Can I follow up on that?
Yeah.
Sure you did. Go back to your last slide. You showed a ratio.
But it's in space.
7 to nothing, right? So if the ratio of the 1 and 2 is 7 to 0, can we take that to be like something that we can relate to the difference in Gibbs free energy?
Yeah, but I think what Professor Johnny was saying is, wait.
The density is too low.
What was your question, Deanna?
What's that?
So you have two models,
Right.
right? And
So you're saying experimental data.
if you put the
shows
experimental
something.
data, what you might find is that that experimental data sits right in the middle, and it's not that Gaussian is better or that Psi is better. If you don't have,
They're just different.
they're different.
But I'll ask a follow-up to that. So at what point did we finally figure out how to get the Psi4 software to actually give us a value that makes sense?
Uh,
Just recently.
Yeah, very recently. So it took us forever to get Psi4 up and running. It took basically 2 terms to do that, and very only recently were we able to get a value that was that made sense with the theory.
The next step is to compare it to find some sort of experimental.
Yeah, and just, you don't want to think of that Gaussian as unknown, because it might just be a different orbital.
I guess what I was trying to say is if the ratio, if the experimental ratio is 7 to 1, then that would say if you plug that into your Gibbs free energy, then I think that's pretty close to your answer, isn't it?
I don't know if they might be directly related in that way.
Okay, because I know like 1 kcal and a half is like 10 to 1. So it's
Right.
like 5, that's like 6 kcal, or 6 kilojoules. So look, 7 to 1 looks to me like single digit kilojoules. In which case your answer is better.
Yeah,
But accidentally. I mean, not because it's,
So perhaps the approximation we made are closer to the real system?
kind of looks like it.
Okay.
But, yeah.
This is taken from, you've got, sorry, now we're.
Well, I mean, no one's arguing that, we accidentally get the right answer with balls and sticks. Like, that's cool. Yeah. No one's saying that, like, we should use Psi4 for everything.
There is data from space, though. I mean, you've got, you should see the resolution.
The resolution is like that.
Why?
Plus or minus 1.
So that's plus or minus 1 for a ratio of 7.
Yeah.
That's actually pretty large.
Yeah.
Yeah.
I mean, I'm not saying it's not, but.
But that might translate into orders of magnitude.
Okay.
Of the rate coefficient.
All I'm trying to say is we can relate energy difference to a ratio. Yes. Right? In theory.
Sorry.
Other questions?
You said that, I thought it was pretty cool that when you were doing your calculations, it spit out vibrational frequencies.
Yeah.
That was awesome. Did you, were you able to compare those to like an actual spectrum of HCN?
Yeah, so we never quite got that far.
Yeah.
But you definitely could.
Because I'm wondering if the paper that did the Gaussian got vibrational frequencies too, if you're going to see discrepancies between the two.
Yeah, so they did, and ours don't exactly match theirs as much as nothing ours matches theirs.
Yeah.
But yeah, you could compare it to actual spectra.
And then follow-up question, how long did it take you to actually run your simulation?
I don't know about total time. Each
Or like to get those vibrational frequencies?
Yeah, so each energy calculation took about only 2 minutes. It's actually, so that's why Cyanide is great. It's pretty simple. So it's not a super long calculation time. So I could run the calculation, change the bond angle, run the calculation, change the bond angle, and so forth.
And would that time change if you had a bigger molecule then?
Yeah, it's changing to a bigger molecule. It changes depending on the approximations you make. So as you get a better approximation, it takes more your processing power, so it takes longer.
So what kind of time are we talking about working? So like other libraries,
Well, depending on what you're doing, you're working as an undergraduate.
Right. Actually, I was graduate student. So my calculations took about 6 months to do.
One calculation. Right.
Yeah, it was
It was a
larger calculation, but a 6-month calculation, if you got something wrong,
That's like what?
you wasted 6 months. And so having this open source tool of computing is
It's especially useful when we're talking about lab development, because you don't want to have students sitting in a lab for 6 hours waiting for their computation.
Sure you do.
Yes.
Maybe along with that is the Psi versus Gaussian software. Is one more user-friendly than another? Or are they both kind of?
I think they both have user-friendly options. So Gaussian also has a nice molecule viewer, as anyone who's taken inorganic organic may know. But I think Gaussian also allows you access to code, so you can be much more specific in your calculations at times. I'm not entirely sure if one is more or less restrictive. Yes.
Karin asked about the frequencies. So the frequency of the transition state look different than the frequencies of the products and outside?
I believe so. I don't know for sure. I don't have to look back at the results.
Okay, so that would be actually the test to see whether it actually is a transition state, because one of your frequencies is going to be imaginary. Because
Right.
if you stretch it, it breaks.
Right. Based on the fact that it's not
Yeah.
nonlinear.
Yeah.
Okay.
So I saw. So your transition state is not symmetrical, right? It's,
Correct.
why do you think that is?
Uh,
Can we make sense of that?
I mean, I suppose it probably has to do with the fact that the two other atoms involved are not the same atom. So it's going to interact, or it'll interact with one more than the other.
Okay.
I suppose.
And so what do you say?
What am I saying?
So it looks like yours is interacting more with the carbon?
Yes. Or it's closer to the carbon.
Okay. All right. It's just different. Awesome. All right.
Any other questions? Yes.
How big were your angle shifts? You said you calculated each angle?
Oh, so I originally used, I'd say maybe a 5-degree changes. When I was actually looking for the transition state, I had basically a guess energy, or I guess confirmation, and then I went in basically 0.5 angle increments to try to find the peak energy around that.
So it didn't have like a find transition state button? Because Gaussian can do that.
No, I'll mention it how I was trying to implement that.
Okay.
Actually, no, yeah, so one of the features of, I think, Gaussian